Alright, hey guys, what's going on? So today we're going to be talking about SU2 interactions, and specifically we're going to be looking at how these SU2 interactions give rise to what we're later going to be calling W-bosons and Z-bosons. This is where really a lot of the stuff gets interesting. So without further ado, make sure to hit that like and subscribe button, and also make sure to hit up my Patreon page if you want to find exclusive content there. On the Patreon page again, you'll find these videos, but appended to these videos are going to be extra long sections where, not extra long, but longer sections where you'll find more derivations to make things a little bit more clear. But anyways, let's get right into the video. Okay, so today we are looking at SU2 interactions. These SU2 interactions are going to be very, very important for what's to come. So we want to really establish ourselves here. So when we defined our global and local transformations, they took the form of this right here, this e to the IA. If it was a global transformation, a was just a constant across all of space-time. If it was a local transformation, a was a function of x, x being our space-time. Here, again, what I'm saying here, where a was a scalar. And this was what we call the U1 transformation, because recall U1 transformations take this form. They're simply exponentials or complex numbers. Okay? Recall that SU2 is another set of representations that could also preserve the Lagrangian, right? So earlier we talked about SU2 preserving the Minkowski metric. They formed the Lie algebra. This is where Lie algebras come back into play, and these SU2 generators, the Pauli spin matrices, are the generators that, or are the matrices, or a set of matrices that represented the Lorentz transformation, or the transformation that preserved the Minkowski metric. The idea here is we also want to preserve Lagrangians. Okay, so what we're doing here, an SU2 global transformation looks something like this, okay? Where A, again, we have this A showing up as not a function of x, right? But now we have these matrices in here. So this thing, this E, this exponential, is actually a matrix, because if you recall, when you exponentiate a matrix, then you get that this is essentially a rotation matrix, okay? These are matrices, the Lorentz transformation representations. Now, that was for this field. For the complex conjugated field, or the conjugated field, we have this sort of transformation where we have to complex conjugate the exponential, okay? So far so good. Nothing is too crazy. So now let's get into SU2 local transformations. So a local transformation is going to look like this. Okay, so we have this u to the x. This x here, this is a unitary transformation. It's a function of x again. Okay, so these guys, I'm saying u just to be a little bit shorter here. The idea again is that these are also U transformations. They're just not dependent on x. X again being the space-time, the space-time. And we do the same thing for our conjugated field, where we have to complex conjugate our operator. Okay? Okay, so we have the global transformations and we have the local transformations. Let's proceed into talking about these guys right here now, because now what we're seeing here is that when this was just a U1 transformation, these things were it was just a one entry object, right? It was just a complex number, okay? But now since this is a 2x2 matrix, we need to make these things are a little bit different now. They need to work with this being a matrix. So, what we're going to say is that this object, has two entries, And these two entries look like this. In the non-conjugated form, it's this, and in the conjugated form, it'll look like this. Okay, so we have a vector, and we have what looks like to be a covector, and things get conjugated also. So we get complex conjugated also if these are complex numbers. So therefore, if we have a Lagrangian or Dirac Lagrangian with these objects, it's going to look like this, right? And if we expand this out, we want this to look, it's going to look something like this, right? Where we have the U1s, the psi1s in one term, and the psi2s in the second term. Combined, we get something like this. Okay, so these here are single entry objects, so complex numbers to say. And these are spinners, right? So, and then here we have two entries. So we need two entries. These guys have two entries. Again, because we need these two entries because these guys are SU2 transformations. SU2 being 2 by 2 matrices. I'll write this out just to make sure things are clear. So here what I'll do is I'll say e to the I a, this is a 2 by 2 matrix. Well, if that's a 2 by 2 matrix, then this thing, this object here must be a 2 by 2 entry object. Okay, so that's what we're saying right here, and we're going to find out what the significance of each one of these objects is later on. I don't want to spoil anything for you guys. This is actually very interesting. Okay, so we now can transform the Lagrangian using a first global transformation. So let's take a look at the global transformation. So we have these guys. We now globally transform them, right? So where AI is just it's just a constant, and again, just a constant here. The only difference again is we have this complex conjugation, and we get this, right? Because since this is not a function of the space-time, this can move across the derivative and things will cancel. So we get this, and this is the same as this, right? The unprimed form takes the same form as the primed form. So that means that this is invariant under global transformations. Okay? Global SU2 transformations. But under local invariance, or local transformations, right? This should be under local transformations. Under local transformations, this is actually different, right? Because now this thing can't move across the derivative. So if it can't move across the derivative, then we get a term that looks a bit ugly. And that term is right here, right? Because, so I'm skipping a little bit of stuff here, but we see here that this d mu is going to apply to this here, which is right here. And it's also going to apply to this guy here, which is right here. And we have, let's see here. So we have here. So this guy, all this right here is right here. Oop. Right here. And right here. The only reason there's no u of x right in here is because when we take the derivative of this guy will come out. We're doing a product rule, basically. We're doing product rule, and it'll cancel here. But when it doesn't come out, it stays on the side of the derivative. So we get two terms in the product rule. One term is going to have the u cancel out with the u dagger. Okay. And so what we're left with is something that does not equal this thing does not take the same form as this right here. So this is a little bit interesting. Under local transformations, our under local SU2 transformations, our Lagrangian is not symmetric. Okay, there's no symmetry when we have local SU2 transformations involved. So we have to fix this somehow, because the name of the game here is keeping the Lagrangian invariant. Invariance in the Lagrangians means symmetries, and symmetries means things that we can actually measure. So how are we going to remedy this problem? So in order to fix this, we're going to invent a new type of derivative such that we want this to be the property of that derivative. We want to be able to move that unitary operator across the derivative in all cases so that we can reattain the symmetry here. Because that's the problem child, right? The problem child is this right here, this derivative. If we can somehow take our unitary operator, that's a function of x, and somehow move it across that derivative, then things will work out hunky-dory and everything will be fine. So we want a derivative that is going to do this. This derivative allows us, and this derivative is going to allow us to move that transformation operator across. So what spin 1 field are we going to use for this? Because if we recall from our last video, we found that if we had a spin 1 object and we had an interaction between that spin 1 object and these other objects within our Dirac field, then we actually were able to attain this movement. We were actually able to attain local symmetry. The name of the game here is, again, we want local symmetry, and what we found was that spin 1 objects actually help in that attainment of local symmetry for the Lagrangian. So in the U1 case, we had these A mu vectors. These A mu vectors, again, describe the electromagnetic field. Okay? In the SU2 transformations, SU2 transformations, in the case of the SU2 transformations, what object are we going to put here? Okay, so there's going to be some analogies going on here between U1 and U2. We're kind of doing the same thing. So the question is, what kind of thing is going to be put here? Well, we're going to put this right here. We're going to suppose that for the SU2 case, we are putting this guy right here. Okay, and we'll talk about what this means. Okay, and this A, so there's going to be A spin 1 vector fields in this case, so that the right hand side is a vector, right? So A's are going to sum over each other, and what's to remain is just a vector, just like the A mu case, or just like in the case of the electromagnetic vector, electromagnetic field vector, analogous to the U1 case. So this sort of begs the question then, if A mu is required for U1 locally invariant Lagrangian, and these guys are required for an SU2 locally invariant Lagrangian, then what are going to be the electromagnetic field tensors, or their analogs, in the SU2 transformation case? Okay, because we want to be complete. We know that there's an electromagnetic field tensor within the U1 case. So again, this sort of begs the question, what exactly are going to be the analogs here? What exactly is going to be the analog between the electromagnetic field case, that's the U1 case, and the SU2 case, right? So here, I have a little mind map. Again, I love mind maps because they really get our things organized for us. But we have A mu. We can construct F mu nu based off of A mu, like this. This is how this thing has been classically defined and proven to be so. And this is our U1 spin 1 tensors, these guys right here. So if we have these guys in the SU2 case, well, what are these going to be? Okay, so we're kind of throwing out some questions right now. The first question is, what exactly is this guy going to be here? And the second question is, what exactly is going to be put right here, the tensor case. So we're trying to figure out what the spin 1 vectors are for this SU2 invariance, and what its associated tensors are going to be like. And we're going to work this all out. We're going to work through the derivations primarily in the exclusive content of this video. However, I'm going to cut to the chase here, so if you decide not to go through the exclusive route, at least you know what the punchline is going to be, so that you can move on for the next videos to come and have this not be too challenging. The idea here is that these objects right here are going to transform in this way. This is going to be the punchline we're going to get to in the rest of this video. However, with that being said, I'm now going to move into the exclusive case, or the exclusive content, again, because these derivations take a long time, and I want to get this right. A lot of research and effort goes into making these, but I'm giving you the punchline here in case you don't want to go through this derivation that's to come. With that being said, I'm now going to get into the exclusive content, which you can find on Patreon.